let's spend a few moments working with Orbital Viewer. We'll look at probability graphs for some atomic orbitals at various energy levels. Remember, these are orbitals for the hydrogen atom, so anything above the 1s would be an excited state for the hydrogen atom's electron. I encourage you to download Orbital Viewer from the internet and take a look at what Dr. Manthey has provided for us. Now we'll move into the Orbital Viewer program, which I have set up with a 2p orbital probability distribution displayed for you. You can see the two lobes of the p orbital. Remember that the two different colors represent the underlying psi function, which can be either positive or negative. One of these colors is positive, the other is negative. They are symmetrical. And remember also that in the center, for the second energy level, you always have an asymptote or node where there is zero probability of finding the electron. Finally, remember that each of these dots represents part of a probability distribution, kind of like graphing a mosquito running around your arm. You can't ever predict exactly where it's going to be, but you know the probability of finding it in a given place. So these very, very rarefied dots around here show a low probability, whereas these very dense dots in this area show a high probability of the electron. The axis for this particular orbital, p orbital, would be running in this direction. We can change the p orbital, and we're going to now go back to the orbital master box, stay on the second energy level with a p, and we're going to change the magnetic quantum number to 0. Remember, it can be -1, 0, or 1 when you have a p orbital. Notice what it does. It redraws, and it's orthogonal to the first one. It's at right angles. Now you see the axis runs this way. The axis of symmetry runs this way, always perpendicular to the node or asymptote. If we then change the display to show the +1 magnetic quantum number, we get the third dimension, and the orbital is going in and out of the plane of the computer screen. Now if we can turn it, we can see again it looks just like the other 2p orbitals, but it is orthogonal to the other two. Let's go back and look at the s orbital on the second energy level and change the p to an s, and m will automatically go back to a 0, but we'll make it do so. And now we can look and see the spherical distribution of the s orbital. We can turn it around in all directions, and it continues to look exactly the same. Again, the probability is low on the outer region and higher as we get in. But right between the positive and negative value of the underlying psi function, you can see this white sphere around the nucleus, which represents the node, which you will always see in orbitals for the second energy level. Let's now move to a new energy level, and we click on orbitals, and we'll go to the third energy level and stay with s electrons and s orbital. Remember, in the hydrogen atom, of course, only the 1s is going to be occupied at ground state. Now in the third energy level, you see that we have expanded the orbital. The orbital is now larger because we've got this third area outside that is what we usually see if we just have one of those hard sphere equal probability distributions. This is spherical. We can turn it around like this or like this, and we see the probability is the same in all directions. There's a spherical symmetry here. We can see the the node between the outer and one of the inner probability distributions for the electron. We're going to have to do a cutaway. This is always a little bit dangerous because sometimes it doesn't quite work. We'll just cut a plane through the 3s orbital. Now we're going to turn it around so you can see that cutaway. See how we cut away? Now you can see more easily the spherical node that exists here. There is another one that you really can't see because I'm not easily able to blow this up. Notice you've got signs changing here around the nucleus, one sign which is the same SIGN as it is in the more visible orange or yellow part, but you've got this little blue area in between as well, and that's where the sign SIGN changes of the psi function. But again, you're squaring the psi function to get these probabilities. So this is the 3s orbital. We'll go ahead and get rid of that cutaway so you can now see the 3p. So now the cutaway is gone, and let's change our display to give a 3p orbital. We'll just show one of those with the 0 magnetic quantum number. Now you can see a little more of a complexity to the 3p. We see again the two lobes that are characteristic of the p orbital, but we also see that each lobe here has a complementary small amount on the other side of the nucleus. Same thing here with the other SIGN of the psi function. It has a complementary on the other side, much lower density, much lower probability. And again, we can turn this p. We can also show on the third energy level, and this is where we will end, the d orbitals. And we're going to change the L quantum number to a d, and we'll go to -2. There's the -2 d orbital. We can see that there are again two nodes at right angles. This looks a lot like what you'd see in a textbook, with one sign SIGN here and the other sign SIGN here. But the probabilities are very symmetrical, and at the nucleus there is 0 probability. If we then change the orbital to -1, we see a similar thing with asymptotes in another set of planes. And we can also go to 0, m is equal to 0. And this is the one that most people think of as d orbital. It kind of looks like a torus or a donut in the middle. And I think it's going to be even easier to see that if we change our rendering options to polygons. And then you can see what you usually see in a textbook. So that's a 3D orbital with this torus or donut shape, because your asymptotes, your nodes, are conical in this case. I hope that helps you to see how these orbitals are shown.